case became psi of r was equal to the incident wave e to the I k dot r minus putting in the Green function lambda over 4 pi d3 r prime e to the I k mod r minus r prime divided by mod r minus r prime, and then a potential u of r prime, a central potential, times psi of r prime itself. Okay. That was the integral equation for scattering. Okay. Lambda is the strength of the potential, and I recall to you that this guy here is related h cross squared times the potential V of r. The potential that appears in the Schrodinger equation is lambda times V of r. Okay. Now this is an inhomogeneous equation, this is the inhomogeneous term, and it is an integral equation. It is called a Fredholm equation of the second kind. So a general equation of the following kind, and I will say a few more words about it. For simplicity, let us look at a scalar variable, just a single variable. So if you have an equation of the form f of x equal to some given function g of x, that is this in this case, in the present case. So some given function plus an integral k of x comma y, some kernel function k of x comma y times f of y dy over some range, some given range a to b. This is called a Fredholm equation. Of the second kind. Okay. An inhomogeneous Fredholm equation of the second kind. Now you can, we will say a lot more about this, at least a little more about this as we go along, but it is exactly of that form. The kernel here, instead of y I have got r prime, the kernel here is some constant times e to the I k mod r minus r prime over r minus r prime times u of r prime, and the unknown function is psi of r prime instead of f here. The given function is this thing here. Now there are equations where if this is 0, for example, if this is 0 on this side, then it says the unknown function integrated weighted with this kernel is equal to some given function here with a minus sign or whatever. That is called a Fredholm equation of the first kind, whereas this is an equation of the second kind. I want to emphasize that it is not an eigenvalue equation because of the presence of this term here. Had this not been present, then it is an eigenvalue equation, and let us for comparison sake put in the lambda here explicitly, then it is an eigenvalue equation, because if this g is not there in abstract form, this thing looks like f equal to lambda some operator on f, an integral operator. Then of course you can see that this lambda plays the role of 1 over the eigenvalue here. That is a Fredholm equation which is homogeneous and it is an eigenvalue problem, but in this case we have not an eigenvalue problem, we have something which has got an inhomogeneous term present here on this side, and the significance of this will become clear as we go along. Okay. Now let us come back here and ask, what is this going to be asymptotically, because remember we want to identify what the value of the scattering amplitude is, what is the scattering amplitude given by in terms of the wave function. So for that we need to extract the large R behavior of this kernel here, and of course you can immediately see that mod r minus r prime, the leading term is r, for r becoming very large, r tending to infinity, in this factor. So there is going to be a 1 over r, which is what we expect, and we would like this whole thing to become e to the power I k dot r plus f of k comma theta e to the I k r over r. That is our asymptotic form, and I want to extract this coefficient f by taking the exact equation here and extracting what the large R behavior is. You can't do the same thing here because this is a phase factor, so you have to retain a little more than this, and notice that r minus r prime is actually equal to r squared plus r prime squared minus 2 r dot r prime to the power of half. That is the meaning of mod r minus r prime, and if I take out an r outside, this is r times 1 plus r prime squared over r squared minus 2 r dot r prime over r squared to the power of half. And now let us do a binomial expansion. The idea being that you are looking at a field point far away from the region where the potential is significant, non-zero. So you have an origin, you have a potential around it spread out in space, but you are looking at asymptotically very far away in a region where the potential's effect is essentially negligible. And in that situation, r prime is certainly smaller than r, much smaller than r throughout the range of this integration, and you can write this as r times, by the binomial theorem, the leading term is going to come from here, the leading correction, because there is an r prime squared over r squared here, but this is the first order r prime out here, first order term in r prime over r, because there is an r here and an r squared here. So the whole thing goes like a 1 over r, and that is equal to 1 minus r dot r prime over r squared. The half cancels against the 2 here, and that is it, the leading term. But therefore, k times this is k times this k times this equal to k times this. Okay. So that is equal to kr, the first term, minus k times r dot r prime over r. Okay. One factor of r cancels and you get that thing there. But r over r vector over r magnitude is just the unit vector in the direction of r. So this is equal to kr minus unit vector along r dot r prime, k times that. Now for a little bit of geometry. If you had the origin here, the origin of coordinates, and there is this potential all round, this was the direction of the incident wave, the polar axis here. Now we are looking at the wave function at some point r in space, some arbitrary point. So you are here, this direction here, that is the point r at which I want to look at the wave function for very large values of the magnitude of r in some arbitrary direction here. That is where my detector is, for example. Obviously that is also the direction of the scattered wave k prime. Remember that the initial momentum was h cross k, and the final momentum depends on the direction you are looking at. There is flux in all directions at all. So this is the direction along which the field point along which you are looking for the wave function, and that is the direction of say k prime here. So clearly, since the magnitude of k prime is equal to the magnitude of k, because it is elastic scattering, this implies that k times Er is in fact k prime, because it is the magnitude sitting here and the radial direction, any radial direction, that is the direction of the scattered wave, that particular scattered wave, okay, the wave vector. So you could go back here and write this whole thing out as approximately equal to e to the I k dot r minus plus e to the I k r over r. The k r comes from here in the exponent here, and then the r comes out from this factor, there is a 1 over r. So e to the I k r over r multiplied by minus lambda over 4 pi and integral over d3 r prime. You can't get away from that because r prime could be small. You have to integrate over all values of r prime, e to the power minus I k prime dot r prime, that is this term here, times u of r prime and then a psi of r prime. Okay. The bracket is closed. So for large values of kr, large compared to unity, this is the factor that multiplies e to the I kr over r, and there is an integration over r prime. So this whole thing is a function of just one quantity, the vector k prime. Okay. And what is the vector k prime? So let us look at the geometry of this once again. You have the incident direction k, and you have some direction with polar angle theta. You are looking at k prime. The magnitudes of these two vectors are the same. The energy is h cross squared k squared over 2m. Incident momentum, scattered momentum is the same in magnitude, multiplied by h cross gives you the momentum, and there is a momentum transfer. So k prime minus k equal to the momentum transfer q, let us call that q, and that is the scattering angle out here. So what is this a function of? This vector k prime is now designated, is now characterized by its magnitude, which is k itself, or the square root of the energy in some units, and the direction, and the direction is precisely the scattering angle theta. Okay. So this quantity here is a function of k and theta, and that is precisely the scattering amplitude, because that is the coefficient of e to the I kr over r. So we have an exact formula, we will come back to this equation, but we have now an exact formula for the scattering amplitude, and that is f of k comma theta equal to minus lambda over 4 pi integral d3 r prime e to the minus I k prime dot r prime u of r prime psi of r prime. This is exact, no approximation at all. The catch is, to find this quantity you need to know the solution to the Schrodinger equation everywhere. Okay. So it is back to square one in some sense. You need to know the solution in order to be able to find its asymptotic form, but of course once you know the solution you can read off the asymptotic form, but you can do a little better than that. But the thing I want to emphasize is that this is an exact expression for the scattering amplitude. So no matter what approximations I make, if I put that in here, I get an approximate equation for the scattering amplitude. Okay. And notice also, as you would reasonably expect, this depends on the potential everywhere in space, not far away, not asymptotic, because this integral is over the entire space here. In particular, it would be strongly dominated by those regions where u of r is large, clearly. So nearer the scattering center there is more contribution in some sense, and we need to be able to manipulate this, but that is an exact answer here. Okay. Now what are we going to do about an approximation? Well, we need to use the fact that this lambda can be tuned, and I said we will keep track of powers of this lambda. So in some sense you could ask a question, okay, what happens if I have a very large kinetic energy to start with, and then I have a scattering which is weak compared to the kinetic energy. In other words, the potential in some sense is weak compared to the kinetic energy. Then I can systematically say that there is an effect due to scattering to first order and then second order, third order, etc. in this coupling constant lambda here. And how would that work? Well, let us go back, because the notation here is a little messy. Let us go back and look at what we had for the Fredholm equation, simply because the notation is easier. Oh, just one small thing before that. Let us try to express this vector k prime minus k, this guy here, the vector q, in terms of k prime and k. So the momentum transfer, I would like to express it in terms of the scattering angle. Now it is immediately clear from here that q squared equal to k squared plus k prime squared minus 2 k prime cos theta. But k prime squared is the same as k squared, so this is equal to 2k squared times 1 minus cos theta. Or if you like, so that is important. The square of the momentum transfer, the magnitude, is related to the energy here, because remember that the energy E was equal to 2me by h cross squared equal to k squared. So we have one relation between the momentum transfer, the magnitude of the momentum transfer, the energy and the scattering angle. So you give me two of them, the third is determined. Okay. So this will also imply that q equal to 2. So if I write this as twice sine squared theta over 2, this becomes 2k sine theta over 2. Okay. And it is a positive number because theta runs from 0 to pi. Okay, that is worth remembering, that the scattering geometry here is worth remembering, that the momentum transfer's magnitude is related to the wave number, the incident wave number, and the scattering angle by this very simple expression. Okay, now let us go back and look at what happens to the solution of an equation like this. Okay. Or if you like, in abstract form, let us write this out as f equal to g plus lambda, some abstract operator acting on f, an integral operator given by the kernel k of x comma y. How do you solve such an equation here? Well, one way to do this is to say this implies that 1 minus lambda k acting on f equal to the given quantity g, which would mean that formally f is equal to 1 minus lambda k inverse acting on g. And now I do a binomial expansion of this inverse operator, provided a certain quantity is much less than 1, is less than 1, right. So this is equal to 1 plus lambda k plus lambda k squared. By the way, this 1 is the identity operator, so let me write it as 1 in this fashion, the identity operator plus lambda squared, lambda cubed, k cubed plus etc. This whole thing acting on f, on g. Okay. When would such an expansion be convergent? Well, it would clearly be convergent. I do not want to erase this, I need to retain this. It would clearly be convergent if in some sense this number was less than 1, but it is an operator, right. So what should be less than 1? The norm of this operator should be less than 1, right. So you would certainly expect this to be convergent if mod lambda times the norm of this operator k is less than 1. Okay. When it is equal to 1, then you have a problem. Then what it implies is that this inverse does not exist. Okay. And when it is equal to 1, what does it imply? It means that this equation 1 minus lambda k acting on some eigenvector equal to 0. In other words, you have hit an eigenvalue of this operator, and then of course this series does not converge anymore. Okay. So if there is a non-trivial, non-null vector in this function space h such that h is equal to lambda k on h itself, right, so that lambda is at a special value, one of the eigenvalues, then of course the resolvent operator does not exist and this solution diverges, does not exist. This is nothing but Cramer's rule in in the context of simple algebraic equations, simultaneous equations. Either the homogeneous equation has non-trivial solutions, or the inhomogeneous one has a unique solution, and the homogeneous equation does not have anything except trivial solutions, right. So that is Cramer's rule, and that is exactly what it is here, except this is called the Fredholm alternative. Okay. So if you are, the assumption is if you are in lambda such that this condition is satisfied, which also implies, by the way, that mod lambda is less than 1 over norm of this operator k. Okay. Therefore, in a sufficiently small circle in the lambda plane about the origin, determined by the magnitude of this norm, this series is expected to converge and provide a solution for you for this equation, inhomogeneous equation. This thing here is called the Neumann series.
So what exactly is the norm of operator?
Now we have an integral operator, so we need to know what the norm of this operator is, right. So what is the norm of an operator in a linear vector space? What is the normal definition of the norm of an operator in linear? If it is bounded, if the operator is bounded, the norm is finite, the operator is bounded. If the norm is infinite, the operator is unbounded. So what do you do? What you do is to take, I do not know what notation you are using, but let us use Dirac notation. So what you do is to take this operator k, act on every vector in the linear vector space. So k on psi, so let us just call it k psi, take this guy here and take the inner product of this vector with itself, but this quantity is 0 if and only if k psi is the null vector, otherwise it is some non-zero quantity, it is in fact a positive quantity, but its value will depend on what the normalization of psi was. You want to get rid of that, so what you want to do is to divide by psi, and then you want to find out what is the least upper bound of this quantity as psi roams over the entire linear vector space, right, or at least the domain of this operator kappa of this k. This least upper bound is called the norm, in this case the norm squared actually, because there are two of them here, so this is the definition. That is for in an abstract linear vector space. What we have, however, is an integral operator. So the first you have to tell me what is meant by the square of this operator, kappa squared, cubed, etc. So what would you say is, this is the operation of k on f, this guy here. What is the operation of kappa squared on this guy? So what would be the representative of k squared on f? What would that look like? It just says take this operator and act a second time on whatever is here, right. So what would it look like? This thing here is represented by an integral. First you take k of x, y, f of y, integrate over dy. Let us call this z for convenience. It is some function of z. Now you take k of x comma z and integrate with respect to dz. And the answer is a function of x. So this is precisely what equal to. In the position basis, this quantity here, this abstract vector, is represented by a function of x, and that function of x is given by this. So you see this form k of x comma z, z comma y, and you integrate over z and you integrate over y with the weight f of y. So that is the definition of the square of the operator. What would be the definition of the norm of the operator? You have to translate this you have to write this out in the position space, in the function space explicitly. Okay. So that is going to involve a modulus of k of x comma y modulus squared dx dy. It is going to right. So that is what the norm is in this case, and then if it is bounded, then this guy here, it says here that as long as lambda is less than 1 over this norm, you are in good shape. Okay. There are specific conditions on this kappa which will tell you under what conditions there are certain kinds of solutions possible, etc. We do not need those conditions right now because we look at specific instances, but this is what the solution looks like, this Neumann series looks like. Let us implement it here, let us put that in here. Okay. What would that mean? It would mean that the first term in the solution f is G itself, it is the identity operator on G, that is already here on this side. And then in this case what you have to do is to take this solution psi and replace it by this series term by term. There is already a lambda sitting outside, coupling constant. So the leading term in this solution, which is of order lambda, corresponds to replacing this psi with just the inhomogeneous term, the G out here. So let us rewrite this equation pretending that you are writing it for psi of r prime. Okay. So for this psi of r prime at this stage, you would write e to the I k dot r prime minus lambda over 4 pi an integral over what? What should I use there as the integration variable?
dr double prime
r double prime, I should use another index, right. So it is d3 r double prime e to the I k mod r prime minus r double prime over mod r prime minus r double prime u of r double prime psi of r double prime. That is exact, no approximations, that is exact, right. So instead of this term I replace it with this whole thing. Now I want the next term in lambda. So you can see now the solution is order lambda to the 0, order lambda to the 1, and then there is a lambda squared times this guy here. And what will be the coefficient of the order lambda squared term? Clearly this thing replaced by e to the I k dot r double prime, and then there is an order lambda 4 term, etc. So this means that your solution is an infinite series which converges for sufficiently small lambda, and it looks like this: e to the I k dot r minus lambda over 4 pi integral d3 r prime e to the I k mod r minus r prime over mod r prime u of r prime e to the I k dot r prime. K is the initial wave vector, and then the next term is lambda over 4 pi minus lambda over 4 pi the whole squared, right. So this next term is the whole squared integral d3 r prime integral d3 r double prime e to the I k mod r minus r prime plus I k mod r prime minus r double prime on that side divided by these two guys times u of r prime u of r double prime e to the I k dot r double prime plus dot dot dot, etc. So that is the formal solution. and you can now pick off this solution to whatever order in lambda you like. I have been a little cavalier about when it converges, except to say that if this norm of k is found, then you can assert that for sufficiently small values of lambda this series will converge absolutely. Okay.
Is it the Dyson series?
One form of it, yeah, the name is not so crucial, yeah. All we have done is to take an inhomogeneous equation and found an iterative solution. In the context of integral equations, it is called the Neumann series. In the context of scattering theory, this is not quite the Dyson series, this is called the Bond series. Retaining up to this point, the first order correction is called the Firstborn Approximation. Now let us come back and look at what it does to the scattering amplitude. By the way, it is very rare that you can take a problem and actually find all the terms in this series and solve it. It is getting clearly more and more intricate out here. There are problems which are solvable, but they are very few and far between, but it is a formal series of this kind. Now let us see what it does for the scattering amplitude though. For the scattering amplitude, we had a formula. So we have f of k comma theta equal to minus lambda over 4 pi and integral d3 r prime e to the I k prime dot r prime with a minus sign, and then there was u of r prime, and then there was psi of r prime. Now let us implement the Born approximation, the Bond series for the psi of r prime on the right hand side. The first term is e to the I k dot r prime, this guy here, and that is already of order lambda because there is a lambda sitting here. So if I use this term in psi for psi of r prime, then I end up with the second order term, order lambda squared term, etc. So this quantity in the Born approximation goes to f, let me denote it by b of k theta equal to the first Born approximation to order lambda is lambda over 4 pi integral d3 r prime e to the minus I k prime dot r prime u of r prime e to the I k dot r prime. So in the Born approximation, what you have to do is to take two plane wave solutions, one with k prime, one with k, and sandwich the u in between and integrate over all space. But you see, you can rewrite this also as minus lambda over 4 pi integral d3 r prime e to the minus I q dot r prime u of r prime, where q is the momentum transfer. H cross q is H cross k prime minus k. This is the final momentum and that is the initial momentum, and the difference is the momentum transferred. What does that formula look like now? What does this look like? It looks like the Fourier transform of the potential. It looks just like the Fourier transform of the potential, with the conjugate variable being the momentum transfer, the wave number corresponding to the momentum transfer, right. In fact, what it does, you can do better than that. Look at what this quantity is. Suppose the initial momentum is an eigenstate momentum vector p here, and you have the potential energy operator here, and you have the final momentum p prime, and you ask, what is this matrix element, right. V is a function of r, So clearly this is some complicated quantity, this is not some trivial quantity. Had these been R's, this whole thing would be just trivial, be just multiplication on a position eigenstate, but we have a momentum eigenstate here, right. Now what is this quantity equal to? Let us try to write this out. This is equal to P prime, and then I insert a complete set of states in between. So let us insert D3 R1, say, let us put R1 just so because I need a large number of indices, R1, R1, and then there is a V, and let us insert another complete set of states. So D3 R2, R2, and then a P. I have inserted two identity operators in between. What is this equal to? This is equal to integral D3 R1, integral D3 R2, and then let us put all these guys together. This is P prime R1 and then R1 V R2 and then R2. But what is this? What is this scalar product for a plane wave, for a momentum eigenstate? It is just a plane wave. That is just e to the I p dot r, nothing more than that. So this is equal to e to the I p dot r2, which is equal to e to the I k dot r2 divided by p is h over h cross, sorry, for dimensional reasons, that is e to the I k dot r2, right. What is this equal to? E to the minus I k prime dot r1. And what is this equal to? You are asking for the matrix element of the potential energy, the operator, in the position basis. In the position basis, the operator does nothing more than multiply by the corresponding function of r, right. So this fellow is equal to V of R2, it is a central potential, and then a scalar product of R1 with R2, but that is a delta function. So this is delta 3 of R1 minus R2. I can therefore do the R2 integral completely, and the answer of course is this quantity becomes equal to integral d3 R1 e to the minus I k prime minus k, that is just q dot R1 times V of R1, and that is it, right. Of course whether I call it R1 or R prime does not matter, it is an integration variable. So it is precisely this, it is nothing but this quantity here. Where was the formula which we had here, over here. So let us put in all this 2m over h cross squares etc., and we discover that this quantity is equal to minus lambda over 4 pi and then 2m over h cross squared, and that guy is precisely equal to the matrix element P prime V of R P. This. Okay. So in the Firstborn approximation, apart from this constant here, the scattering amplitude is nothing but the matrix element between the initial momentum and the final momentum eigenstate of the potential energy operator. Okay. That is an easy thing to remember. Of course if you want the subsequent corrections, then you have to put in a non-trivial wave function here, you have to put in this second order term etc., etc. Okay. But let us see where that gets us. Let us look at some simple examples and see where this thing gets us. Now the idea is that if some lambda is sufficiently small in some sense, then the firstborn approximation is good enough. So let us see where that will get us. Let us look at some typical cases. Now you could do all kinds of problems. We could look at hard sphere potentials, we could look at Yukawa potentials, Coulomb potential, etc. Let us look at a very famous potential called the Yukawa potential. So let us look at lambda v of r equal to lambda times e to the minus exponentially damped with some length scale xi, say, over r, where xi is a positive constant. Okay. This thing is called a Yukawa potential. It is a central potential for which the radial Schrodinger equation is not expressible in terms of elementary functions. You can't solve this very easily. It is called Herne's equation. You can in principle write it in terms of some special functions. We are not interested in that here. We want to know what is happening to the scattering amplitude in the Born approximation, which will be guaranteed to be valid provided lambda is sufficiently small. There is a length scale in this problem that is given by xi, characteristic length scale. So we need to play with that. But before we do that, let us take that formula and run with it a little bit and see whether we can simplify it a little bit, because it is a little messy as it stands. So let us see if we can do some of this integration. So f bond of k comma theta is equal to minus m lambda over 2 pi h cross squared, and then this integral integral d3 r prime, d3 r I might as well call it r, e to the minus I q dot r u of r, v of r. Okay. I need to do this integral here for a given q, for a given momentum transfer here. What coordinate system should I choose?
Polar.
Spherical polar coordinates. Along which direction should I choose the polar axis?
Q.
Along q, because that vector is sticking out, so I choose it along q. Then the phi integral gives me a 2 pi as always, and this is equal to minus m lambda, and this 2 pi cancels out and you get h cross squared. The phi is gone, and now I have integral 0 to infinity dr r squared, that sits here in this case, and then e to the minus I q r cos theta, and cos theta integrated minus 1 to 1, right. So this is equal to minus 2i sin q r over minus I q r times v of r, right, and that is equal to, so the I cancels out, and then it is equal to 2m lambda by h cross squared q with a minus sign, and then an integral 0 to infinity dr r v of r sin q r. Now that is a very simple formula. So you give me a v of r and I integrate it and do this integral. That is the scattering amplitude in the Born approximation. The mod squared of it gives me the differential cross section, and after that I have to integrate over theta to get the total cross section in the Born approximation. So let us apply it to this Coulomb potential and see what happens. So this thing here becomes f of k theta, f bond of q theta becomes minus 2m lambda over h cross squared q, and then an integral from 0 to infinity dr, there is an r sin q r, and then e to the minus r over xi over r, and obligingly this r cancels out. That integral, of course, we know the value, this guy here. So what's this equal to? Minus 2m lambda over h cross squared q. And what's the value of this integral? E to the minus ax sine bx. No. How do you do those integrals? You learned this in first year calculus or something like that.
1 by 1 plus dice.
Integral 0 to infinity dx e to the minus ax sine bx or cos bx. What are the values of these integrals? You have to integrate by parts and then you bring it back and so on. So what do you get at the end of it? You're stuck on a desert island, you don't have anything, no tables of integrals, nothing, no Mathematica, nothing. What do you do? Well, this integral is b over a squared plus b squared, and this integral is a over a squared plus b squared. Right? No? I mean, all you have to do it's the imaginary part of this guy here, right? So write this as e to the minus a minus ib, and that's equal to the imaginary part of 1 over a minus ib, which is equal to b over a squared plus b squared. Okay. And the cos of course the cosine is a over a squared. How do you remember which is which? If you had a cos here, then the answer would be a over a squared plus b squared, the real part. And with the sine, but I mean sort of doing this each time, how do you remember which is which? What happens to this when b is 0? It vanishes, right? When a is 0, what happens?
1.
Then you are very tricky. But when b is 0, it vanishes, the sine, but the cosine does not, right? So whatever vanishes, that must be the sine. This is sine, the other guy is cosine. So anyway, this thing here is equal to q over q squared plus 1 over xi squared, and the q cancels out. That's it. So that's the explicit representation in the Born approximation for the scattering amplitude from a Yukawa potential. Okay. Now let's write this back in terms, sorry, this should be somewhere along the line I made a little mistake in notation. This was a capital Q everywhere. So this is a capital Q. This guy was a capital Q. Square of the momentum transfer, right? So this implies that the Born, in the Born approximation, f of k theta equal to minus 2m lambda over h cross squared, and then 1 over, and what's q squared? Remember it was 2k squared into 1 minus cos theta plus 1 over xi squared. Okay. So that gives you the exact dependence in the Born approximation on the angle as well as the energy as well as little k. So calculate d sigma d omega and sigma total from this. The mod squared of this is d sigma over d omega, and then you have to integrate it over all solid angles. That is theta from minus 1 to 1, I mean from 0 to pi, and phi over 0 to 2 pi gives you just a factor of 2 pi. So that gives you the total cross section, and express this sigma as a function of c. Find the total cross section as a function of the energy. going to depend on k, so it depends on the energy, and show that for very large values of the energy it actually drops like 1 over E, very characteristic. Okay. Now we can do a little more. We can actually do what the Coulomb potential does, and that is a little tricky, because suppose I had the Coulomb potential, what was this integral actually? This was equal to dr, there was an r here and there was a v of r here in general. Now for the Coulomb potential you end up with just a 1 over r that cancels this and gives you an integral over sine qr, which does not exist as it stands, because this function oscillates back and forth, right. But you can still make meaning out of it by saying, oh, the Coulomb potential is the xi going to infinity limit of this Yukawa potential, because as xi tends to infinity this goes away and you end up with just a 1 over r, and that we can extract, the xi tending to infinity limit of this. So this guy here goes, xi goes to infinity to f bond k theta for the Coulomb potential, and what is that equal to? That is minus 2m lambda over h cross squared 1 over, so let us put all these fellows in, and then you have a 2k squared, so that gives you a 4 k squared sine squared theta over 2, and this is 0 out here. Now what is k squared? It is 2me over h cross squared, so let us put that in here also. This is equal to minus 2m lambda over h cross squared 1 over 4 times 2me over h cross squared, which is up there, and then sine squared theta over 2, and the h cross squared cancels, the 2m cancels, right, and then you end up with this statement that in the Born approximation k theta modulus squared equal to d sigma over d omega for the Coulomb potential, d sigma in the Born approximation. Okay. This is equal to the mod squared of that fellow, which is lambda squared over 16 e squared sine to the power 4 theta over 2. Does this ring a bell? This is the Rutherford formula for scattering from a Coulomb potential. It is precisely the Rutherford formula. Many remarkable features of this formula. The first one is we have evaluated it in the Born approximation in quantum mechanics, but it happens to be the exact classical answer. It also happens to be the exact quantum mechanical answer in this case, because the higher terms vanish in this potential, although we have not proved that here. And what is most remarkable about it is that it is a quantum mechanical scattering problem, but there is no Planck's constant. Okay. So Planck's constant has completely disappeared, which is why it makes sense to say it is also the classical answer, because otherwise there is no chance of coinciding. And it is exact, this formula is exact. There is this famous cosecant to the 4 theta over 2 sitting here. What does it do as theta goes to 0? It blows up, right. This means the forward scattering amplitude is blowing up, and of course the total cross section will blow up, because you integrate this is not an integrable singularity, that also blows up. Now the reason for that disease, the fact that this scattering cross section blows up, the forward scattering amplitude blows up, etc., is that the entire formalism that we started with is not valid for a potential which goes to 0 as slow as 1 over r. It has got to go to 0 faster than that. The moment it does this, then the assumption that the initial state was a plane wave state is no longer valid, because the potential really acts everywhere and you have to be much more careful. You have to start with a proper initial state, which turns out to be an exponentially modulated plane wave state. So there is a plane wave state which is modulated, and we have to use that. There are logarithmic corrections and so on, phase factors, and when you do that you get an exact scattering answer. You get an answer for the Coulomb problem very rigorously. Okay. But the fact is that the Yukawa potential actually in the limit as I goes to 0 ends up giving you the correct Rutherford formula here. Now by the way, a word about this Yukawa potential. In quantum field theory, the forces between particles are mediated by what are called gauge fields, okay, and they are mediated by the quanta of these fields, and in the case of electromagnetic interactions it is photons, and the photons have 0 rest mass, and that is what corresponds to xi going to infinity in 0 here, okay, because this quantity here has the dimensions in the static non-relativistic approximation. This exchange of particles in quantum field theory will lead to a static potential of the Yukawa type, in which this quantity here has the dimensions of the Compton wavelength of the exchange quantum, okay. And what is the Compton wavelength? It is h over the Compton momentum, and if the rest mass of the particle is mu, the Compton momentum is mu c. So this guy here is h over mu c, and the mu goes up on top, and it is the rest mass of the quantum, and in the case of a photon that is 0. So that disappears, becomes unity, and you end up with the Coulomb potential here, okay. So there is a direct connection between the rest mass of whatever is exchanged and this phenomenological Yukawa potential, the form of this potential, okay. And the Rutherford formula, as you know, is valid in the case of electromagnetic interactions because the exchange quantum is the photon and its rest mass is 0. So that is why you get a Coulomb potential from a Yukawa potential. Now we can do this in the case of other potentials also. In fact, I urge you to do the following, do it for the following potential. So take B of r to be equal to V naught, some constant, for 0 less than equal to r less than equal to some a, some fixed number a, and 0 for r greater than a, and find fb of k theta sigma, the cross section in this case, okay. So this is like saying that I have a potential barrier and I scatter off this barrier, and also do this for V of r to some V naught, some constant. We do not need that constant here actually, because we can absorb it in lambda, delta of r minus a delta function at some value a, okay, and nowhere else, just a spherical shell, and you find out what the scattering cross section is.